Assalamualaikum. My name is Nur Khairunnisa from AS2436. Today I will present the final year project 2 with title Effect of Polyhydrate Solution, Transesterification Reaction of Waste Cooking Oil Based Polyol as Polyurethane Precursor. Background of study. Polyol are compounds used to produce polymer precursors such as polyurethane. Polyol are mostly derived from petroleum, a non-renewable resource. Petroleum refining may harm the environment and pose risk to human health and ecosystem. Polyol can be generated from various natural resources, including vegetable oil, animal fat, fish oil, and carbohydrates. Problem statement. First, the use of polyol derived from waste cooking oil has been limited due to insufficient research into their viscosity and other properties in polyurethane precursor composition. Second, two methods were explored to produce biopolyol, which is a two-step process involving epoxidation and oxygen ring opening with diethylene glycol, and a single-step transesterification using titanolamine. The objective of this thesis, firstly, to synthesize polyol from waste cooking oil (WCO) using the transesterification method by different formulation of polyhydrate solution used. Second, to investigate the chemical properties such as hydroxyl, OH value, acid value, and free fatty acid content of polyol produced by waste cooking oil. Lastly, to determine the characterization and physical properties of waste cooking oil polyol-based polyurethane. What is waste cooking oil? Waste cooking oil, WCO, is a sustainable resource that may be used to make biodegradable polyol. Considering its production from recycled material and sustainable manufacturing technique, this material presents the potential for reducing carbon footprint. It is significant because the use of WCO lowers the higher cost of producing biodiesel. It resolves issues related to WCO dispersal, and it does away with issues related to contaminating aquatic and terrestrial environments and clogging drain and pipeline due to improper disposal. The most efficient method for producing waste cooking oil is to filter and treat the WCO before synthesizing into the WCO polyol. Polyol derived from WCO. First, polyol derived from waste cooking oil WCO are gained the attention as a sustainable alternative for producing polyurethane and other polymeric materials. These polyol are synthesized through chemical modification of triglyceride and free fatty acid in waste cooking oil, making use of an abundant and often discharged resource. Second, the polyol method, which contains polyol solvent having more than 2 hydroxyl group, is convenient since pressure can be applied without the need for specific equipment or separate calcination or ignition following wet synthesis. What is polyurethane? Polyurethane is a type of polymer known as polyurethane, often a shortened of PUR or PU, is made up of organic units connected by carbamate, which is urethane, linkage. Unlike other less used polymer like polystyrene and polyethylene, polyurethane may be made from a variety of precursor ingredients. Polyurethane, which is PU, find application as paint or coating PUC, adhesive foam PUF, and elastomer. Because PUC has excellent abrasion resistance, corrosion and chemical resistance, and low temperature flexibility, and it is used in a wide range of applications from automobile finishing to industrial maintenance or furniture application. They are used in various industries. PUC can be generated in 3 ways: waterborne, solvent-borne, and solvent-free. Synthesis of WCO oil-based polyol. The shift from a fossil fuel base to a renewable energy based economy with bio-based feedstock utilized in the production of materials, energies, chemical and reaction is a crucial part of sustainable transition. The impact of biomass as a feedstock on this paradigm, the production of polyurethane by chemical firm is viewed as go green. The environmental benefit of vegetable oil, such as their cheap cost of extraction, biodegradability, and non-hazardous handling, have drawn the attention of various research who are looking to use them as a polyol in the production of polyurethane. Material use. Waste cooking oil, WCO, is collected from homes and used as a raw ingredient to synthesize polyol. The polyhydrate solution for the transrification method in producing WCO polyol use the combination formulation of tritanolamine TEA, ditennolamine DEA, potassium acetate PA, monoethylene glycol MEG, diassociate of 2,4-diphentylamine MDI, and lastly dibutylene dilaurate DBTDL. Pre-treatment WCO. Start with filter WCO, heat within range 55 degrees Celsius to 125 degrees Celsius, and added activated carbon while heated. At the same time, stir for 1 hour at 500 RPM at 110 degree. Filter again using filter paper. The preparation of PU. Start with mix polyol with MDI until mixed well at 80 degrees Celsius. Adding DBTDL. Add dissolved mixture at 80 degrees Celsius for 1 hour and pour into petri dish. Dry overnight and post cure at 60 degrees Celsius for 24 hours. Transesterification. DA-MEG-PA mixed with ratio 90:7:3 and mix solution left overnight at room temperature. Add anhydride solution and heat for 185 degrees Celsius to 195 degrees Celsius for 20 minutes and continuously stir. For the acid value, mix 10 gram purified oil with 50 ml ethanol. Add 2 or 3 drops of phenolphthalein. Pour ethanol into the sample and shake. Boil mixture until completely dissolved. Add 3 drops of phenolphthalein and titrate with 0.1 and NaO dropwise until turn into light pink and record the final reading. OH value. Dissolve 1 gram of waste cooking oil with 20 ml phthalate anhydride, which is pyridine reagent. Allow to cool at room temperature for a few minutes. Rice condenser with 30 ml pyridine and edit 0.5 and NaO dropwise until turn into light pink color. For FTIR, ATR method introduce light onto a sample and allow it to be measured immediately for ATR or FTIR to provide composition and structural information. Use Perkin element spectrum 100 to record spectra with wave number ranging from 450 to 4500. Acquire the parameter with a total of 16 accumulation at 4 resolution and a spectra range of 4000 to 650. Result for synthesis of waste cooking oil WCO and WCO polyol. FTIR spectra show structure difference between WCO and WCO polyol. The strong carbonyl C-double-bond-O peak at 1743 in WCO is weaker or slightly shifted in WCO polyol, indicating partial conversion for ester group into hydroxyl group. Both spectra have aphatic CH stretching band at 2920 and 2855. Though their strength varies due to chemical change, the WCO polyol spectrum also shows stronger CO stretching peak, range 1000 to 1200, suggesting the formation of ester or hydroxyl group. This change confirmed WCO's successful transformations into polyol, essential for polyurethane synthesis. Synthesis of waste cooking oil to produce polyol. Acid value for raw WCO 0.8 gram per mole, pre-treatment WCO 0.72 gram per mole, WCO-based polyol 0.52 gram per mole. Free fatty acids for raw WCO 0.4024%, pre-treatment WCO 0.3622%, WCO-based polyol 0.2817%. OH value only have for WCO-based polyol, which is 200 to 400. Color for raw WCO, dark brown. Pre-treatment WCO, light brown. WCO-based polyol, brown. Synthesis of WCO-based polyol as polyurethane precursor. Comparing the FDIR spectra of polyol A, which is DEA, MEG, PA, and polyol B, TEA, MEG, PA, show notable structure difference. Both have a strong OH peak, but polyol B peak at 3331 is sharper than polyol A border peak at 3329. The CH searching region differ with polyol B at 3006 and polyol A at 2853, indicating change in the hydrocarbon structure. Both show a carbonyl C double bond O peak at 1744, confirming ester or carboxyl group from phthalic anhydride. In the NH bending region, polyol B has a peak at 1690, while polyol A's smaller peak appear at 1575, reflecting difference in hydrogen bonding due to amide type. The CO stretching peak at 1160 suggests ester or ether bond with minor change. This variation show that while both polyol share similar functional group, the choice of amide TEA or DA affect chemical bonding, particularly in the CH and NH region, potentially influencing material properties. Solubility behavior of polyurethane. DBTDL is a strong G-line catalyst with high thermal stability and activation energy, allowing fast curing even at room temperature. In polyurethane formation, the reaction between polyol alcohol groups and isocyanate continues until a cross-link system forms, reaching the gel point where mechanical strength develops. Toluene, a strong organic solvent, can soften, swell, or dissolve polyurethane by breaking intermolecular bond. This solvent induce degradation occur through polymer change scission, with notable deterioration seen after 24 hours in toluene. For the conclusion, the process of turning WCO into polyol and then into PU show great progress in sustainable material. Pre-treating WCO and converting it into polyol with lower acid and free fatty acid value help control the polyurethane performing process. The OH value range 200 to 400 mg/kOH per gram supported successful PU production. FDIR analysis confirmed polyol formation with an OH peak at 3331 and PU formation with an NH peak at 1690, along with the disappearance of NCO peak at 2275. A swelling test showed that polyurethane fully degrades in toluene, indicating that the soft segment from polyol was compatible with toluene, formatting swelling and degradation. For recommendation, future studies show improved polyurethane strength and resistance to swelling by adjusting reaction factor like catalyst ratio, curing time, and adding cross-linker. Using reinforcing agent or new curing method can further stretch the material. To expand industrial use, the process must be scaled up while ensuring it remains eco-friendly and cost-effective. That's all from me. Thank you.